All right, maybe we'll get going. If I keep this, morning everyone. If I keep these lights, is there enough light for everyone? I'll just try to get a balance between seeing the screen and having enough light to see. Yep, everyone's happy with that, the lighting? Okay. Before we go on, is there any questions about the prac yesterday? So that was really just a gentle introduction to ArcGIS. I hopefully gave you a bit of a sense for what it looks like and some of the things it does. If you haven't used it before. No? No questions? Everyone got through it okay? Yeah? Okay, good. Right, so what I'm going to do, as I said, we're going to have, each day we'll have a quick quiz to start with, and so we're going to do that first. And the idea is just to give you a bit of reminder of what we did the day before, and a bit of feedback. You know, if there's and really, I guess, some feedback to see how you're going in terms of whether you sort of understood the concepts. So I'm going to give you a little clicker. Each person will have a little clicker, and so the idea is we'll just give you multiple choice questions on the screen, and you can click and answer with a little clicker, and we'll see people's responses. And you know, it's useful, I think, because if everyone gets it wrong, then we can have a discussion about that and resolve anything that people don't quite understand or misinterpreted. So that's really the idea of these quizzes. They're just a bit of fun, really. So what I'll do, maybe we'll just spend a couple of minutes just passing these things around. There's these little clickers. So what I'm going to give, I'll give everyone one of these. Hopefully I've got enough. I think there's about 54 in the class, so I didn't count them, but it looks like there's enough. Anyway, we'll if there isn't, we'll make sure we get some for the rest of the week. So what I'm going to do, give you these, just hold on to them for the course and just bring them to each lecture. Okay, and I'll collect them back off you after the last lecture. Okay, so just remember to bring them in. Okay, so I might why don't I just grab some and just pass the box around, and they should all work, I hope. 1, 2, 4. Can't count. That's 4. Sorry. I was going to grab a few. I don't know whether we're going to have enough. Anyway, we'll see.
Thank you.
Got enough there? Got one for everyone? Yeah. We might just have enough. Did you have any here? Oh. Did you have some? Yeah, we haven't quite got enough. I'll have to get some more. So some will have to go without, I'm afraid. But that's okay. I'll sort that out. So if anyone doesn't have one, we'll make sure we get some for later in the week. Yep. Sorry? We've run out. Yeah, they were 100, but obviously, so I thought we'd have enough. But I'll get some more, so don't worry. We'll sort that out for later in the week. Sorry. Okay. So I guess that box used to have 100 of them in, so I thought we'd have enough, but we obviously don't. So there's probably maybe a handful of people who don't have one. I think there's, wait a minute, there might be a couple more here. No, sorry. But I'll get some more. So who doesn't have one? Put your hand up if you don't have one. Yeah, okay, that's fine. So put your hand up if you don't have one. I want to know how many more to get. 1, 2. Just 2? 3? Okay, so if I get 10 more or so, that should be enough, right? Okay, I'll try and do that. Same. Okay, so we'll do. So basically, we'll. Yeah, hang on. So we'll just have some. There'll be some multi-choice questions, and we'll just go through them one by one. So yeah, so keep hold of them, don't lose them, and on the last lecture, I'll just collect them all up again. Okay. Or at least try not to lose them. It just takes a few minutes to, 30 seconds or so to load. Okay, so hopefully this will work. We'll see how we go. So so they'll come up just like this, and then you just need to choose an answer. So they will have 5 questions each day. So the first question here is the main reason for using GIS in urban planning is A, to store spatial data, B, to communicate using maps, C, to conduct complex analyses, or D, to predict species distributions. So just choose one. You should be able to choose A, B, C, or D. And, oh yeah. Okay, so I'm getting some responses, so it's working. At least some people's are working. And then we'll just see people's responses. No, they should just be on. Yeah. Yep. They should just be on all the time. All right, so we've got some, I've got about 35, 40 responses. Okay, we'll see what people answered. Okay, so it's a bit small, isn't it? But anyway, so these are your answers. I mean, so half of you said to conduct complex analyses. Some of you said to store spatial data, communicate using maps, and then a small proportion said to predict species distributions. Actually, all of those probably would apply. So they're all right. So everyone's right. I mean, I think you use GIS to store spatial data. That's certainly true. So local councils, for instance, will use a GIS to keep spatial data. Certainly communicate using maps. I showed you an example of that yesterday. Being able to communicate interactively data for the city of Perth. So another example of communication. Communication is a really important aspect of GIS. Conduct complex analyses, yep, certainly. So if we're looking at trying to understand relationships between urban plans and maybe environmental values or other things, soils and so on, then we can use GIS to understand those relationships and inform planning. And possibly we could use this as well. If we're interested in impacts of urban development on species, we might want to understand first where species distributions are. So, so actually all of them would apply. Yep. I can probably make them available. Yeah. Yeah. Do you want to? You'd like to see them, would you? I will work out a way of making them available to you. Yeah. One option is I can just put them into a Blackboard quiz, and you could use them from there. Yeah, but it will take me a bit of time to do that. So, yeah, I'll try and do it over the next week or so. Yeah. Okay, that's fine. Yeah. Okay, next question. So, actually, did we? Yeah. Okay. So this is a big test from yesterday. What is Tobler's first law of geography? Near things are more similar than far things. Toblerone is the best chocolate. Scale matters. Geographic analysis is primarily about detecting trends. All right, I think I got most people's responses. Let's see what people said. Yeah. Yeah, so most of you got that right. So it is this idea that things that are close together tend to be more similar. And I think using that idea, we can say a lot about what's happening spatially and try and interpret patterns. So, yep, good. You remember that? Excellent. You were listening. Cool. Okay. So which of the following questions is best answered using GIS? What is the price of ice cream? How old is that tree? What is the age structure of a population of Saiga antelope? And where are the best places to find iron ore? So I guess in answering this, think about what GIS does. Okay, I think I've got most responses. Yeah, so most of you got that right too. This is the only one with a spatial component. So really, GIS is used for answering spatial questions. The others have, well, I mean, the others really have nothing to do with space. So, you know, these things might be data or attributes that we use in a GIS analysis, but they're not spatial in themselves. Okay. Good. Excellent. So this is a bit of a test of history for you. So the first GIS, the Canada Geographic Information System, enabled which one of the following things primarily? Calculations of distances, calculation of areas, population sizes of threatened species, not spelt right, or height of trees. Okay. Yeah. So most of you got that right as well. It was calculation of areas. I mean, really, that was a time-consuming activity. So before GIS, people used to use these dot maps, put over a clear sheet of paper over a map, put dots on it, and then of the area you want to calculate, and essentially add up the dots. Very time-consuming process. So one of the things that drove that innovation was just, if you've got vast amounts of data, how do you actually calculate areas? And you know, then it wasn't trivial, and being able to use computer technology at that time to calculate just areas of things was a massive advance. So that was the initial driving force for GIS, and obviously area is a spatial aspect. Okay, make sense? Yep. Calculation of distances sort of came later. Okay. So which one of the following is not a component of a GIS? People, network, software, or books? I'm thinking of that broad definition of GIS. Yep, good stuff. Yep, books is, well, not really an aspect of GIS. But yeah, so there is this idea of GIS being a broad network or a broad connected system of people and software and hardware procedures all connected through a network. And GIS is increasingly becoming so. Okay, any questions about that? So that's 5 questions. We'll do that each morning. As I said, it usually takes us about 15 minutes or so just to kick things off. So it will get a bit harder, I think, as we go through the course. So, yep, good. Any questions about that? Nope. Nope. Okay. All right, let's kick on with today's lecture. Everyone hear me okay? At the back there? Yeah? So today's topic really is giving you some of the really basic building blocks of GIS, and we're going to talk really about two ideas really. One is how do we represent objects spatially, and then how do we represent where they are on the Earth's surface. So two basic aspects. So this is conceptual in a way, and really giving you those building blocks for thinking about how we represent spatial objects in a GIS. I've put, if you look at, if you want to look at the readings, you should look at the readings. So there's two chapters. Well, there's a couple of chapters from the Jensen and Jensen book, and if you don't have access to that, there's a couple of equivalent chapters from Campbell and Shin if you have access to that, and that one's available. I've put that under learning resources on Blackboard. So do make sure you do the readings if you haven't done them yet. But yeah, hopefully the readings are not too onerous. They're relatively easy to read, those two books. Okay. So the first part of the lecture, we'll have maybe 20 minutes, half an hour of content, and then we'll do a short exercise. So the first thing I'm going to talk about is how do we just represent geographic objects spatially, and these are things called data models. So a data model is really a way of representing a geographic object, be it it could be a tree, a house, a person, a road. So these objects spatially, but it could also be other things that are less well defined spatially, such as rainfall or temperature or atmospheric pressure. Characteristics of soil types that vary sort of more continuously across landscapes, but it's really both of in this case the data model is really a conceptualization of the world, and that we translate into a digital representation that allows us to represent objects spatially in a GIS. So we're going to look at that conceptually about what a data model is, and then look at what the different data models are that in a GIS, or the typical ones that we use to represent different objects. So as I said, it's really basic building blocks of GIS. But I think it's important to get this concept right. If you've never come across these before, important that you understand where they come from and why. Okay, so I'm going to ask you a question first. If we think about how we what we're doing in a GIS is really trying to represent the real world in a digital form, and we might. So what I'm giving you here is 2 pictures of the same landscape. Okay, this is a landscape from the same landscape from up on a hill. So you can see different land cover types, a dam, and this is the same landscape but zoomed much further in. Okay, so this is within one of the forest patches, and so we wanted to represent this landscape in a GIS. What are some of the challenges of doing that? What's hard about it? Yeah, it's really complex. So this might not look all that complex, but once you zoom in, actually, it's actually really complex. So here you could conceptualize it as agricultural fields. You've got some forest cover. You've got a dam. You've got some roads. So you can conceptualize it that way. But if you zoom in, actually, there's much more complexity than you can see in this image here. So, and if you zoom in, there's different types of trees, different species, different sizes of trees. There's logs on the ground and wood. There's structure in the in the understory and so on. So there's a lot of complexity, and you can zoom in further and you get more and more complexity. So that's right. So if you if you think about it, the world's an infinitely complex place, and whatever. I'm going to talk about scale a little bit tomorrow as a spatial concept. But basically, by looking at that landscape from that distance compared to that distance is really an issue of scale. So this is a much finer, what we call a much finer scale or resolution of looking at the landscape. But you can, at finer and finer scales, the world becomes more and more complex. So the world's an infinitely complex. It's almost impossible to represent all that complexity in a GIS. We don't have enough computer power. We don't have enough storage to represent all of that complexity. We usually don't have the data either. So I might quickly show you. This is a I don't know whether this will work, but we'll see. Bear with me a second. It's a bit slow. Okay. Okay, so this is just a little app or API that, or a little image that basically starts from 10 million light years away from Earth and then zooms in powers of 10. And I guess is a nice illustration of how the complexity of the universe and the world. So sort of illustrates the point that depending on which scale you look at the world, there's infinite, large amount of complexity. Okay, so it's just an illustration of depending on the scale at which you look at the universe, and if you think about this complexity at all those different scales, you've got a huge amount of complexity that we simply just cannot represent entirely within a GIS. Okay, so hopefully I've convinced you that the world is complex. Right. So what we usually do in creating data models for a GIS is abstract the real world, and we simplify the real world so a computer can understand it, and we can visualize the world. So I guess geographers realized this early on that actually it was almost impossible to represent all of the world's complexity. So they had to devise ways in which to simplify the world to represent them. And initially that was on maps, but then subsequently digitally in a GIS. And there's two ways geographers have used, tried to do that. And one is using a thing called continuous fields, and one is a thing called discrete objects. So continuous fields sort of represent things that vary continuously. And then discrete objects are representations of things that really have discrete boundaries, where they've got well-defined boundaries, essentially. Okay. So what are some examples of can you think of something? I'm going to talk a bit more about when we use one or the other. But you got some examples of when you might use a continuous representation versus a discrete representation? What might you use continuous representation for?
Something that changes over a spatial area.
Yep.
So
Yep. Elevation. Yep.
Temperature.
Yep. Yep. So those things that vary continuously. Yep. So and that's true. And usually we do use that to represent those. You'll see in a minute that we can use it also to represent discrete things. But yeah. So what about discrete objects? What types? Have you got some examples of things that we might represent as discrete objects? Land use type. Yes. Yep. That's a good one. Anything else?
Anything that can be clearly categorized.
Yeah. Such as.
Either presence or absence.
Yep.
High elevation, low elevation.
Yes. Yep. So actually, taking your example, you can discretize those things if you want and represent those discrete things, and that we can do. So actually, we can almost represent even with the discrete representation, we can represent continuously variable things. But anything else? Yeah. I mean, there's buildings. What else? Pretty much, things that have where you can clearly define a discrete bound, or a boundary is usually when we use discrete objects. So that's sort of the idea, but there's this blurring of sometimes you can use the continuous representation to represent discrete things, and discrete things to sometimes represent continuously varying things. But if we want to formalize when we use one or the other. So are people familiar with interval ratio nominal and ordinal data? No? Do you want me to go over it, what they are? Yep. Okay. So I've put a link down here if you want to read more about what they are. So this is really a way of trying to classify data types. So when you're representing things in a GIS, they'll have a spatial location, but they'll usually have attributes. And the attributes will describe what they are. So if it's if you've got objects that are representing things on a street, it might tell you things. Whether it's a lamppost or a traffic light, for instance, and so the attributes of the things really describe what the object is. And when we use continuous fields, we usually use them for things that are called interval and ratio data. So these are continuously variable attributes, such as rainfall, temperature, and so on. But there's a distinction between interval and ratio data, and I'll try and get this the right way around. Interval data basically is continuous values that don't have a natural origin, so they don't have a zero value. So an example would be temperature. So 0 degrees Celsius isn't particularly meaningful. We just decided that at that temperature we're going to call that 0. So 0 doesn't actually mean anything as such. So it doesn't have a natural 0 value. And we could have put the 0 anywhere else. We could have put the 0 at 10 degrees. It would still be the same. And so with interval data, the difference between values matters. So you would say 10 degrees is 8 degrees warmer than 5. No, sorry. 10 degrees is 5 degrees warmer than 5 degrees, but you wouldn't say that. But the ratios don't make sense. So you wouldn't say 10 degrees is twice as hot as 5. Okay, that doesn't make sense, but because it doesn't have this natural 0 value. Okay, so with interval data, differences between values make sense, but ratios of values don't make sense. Ratio data does have a sensible 0 value. So, for instance, height is an example of ratio data. So 0 height is truly 0 height, right? That's a sensible 0 value. So then in that case, the ratios make sense. So you can say a building that's 10 meters high is twice as high as a building that's 5. That statement makes sense. So dividing one value by the other gives you that ratio. So that makes sense. Okay. So that's the distinction between these. In most cases, it doesn't really matter but you would never, if it's interval data, you'd never divide one number by another. You would only do that for ratio data. So I think for ratio data, dividing one number by the other makes sense, but also the difference makes sense as well, okay? But not for interval data. But in most cases, it won't. For the implementation of the data model, it doesn't make any difference. And then, for continuous fields, it's where these values vary continuously over geographic space is usually where we use them. But as you go through the course, you'll see exceptions to that. Okay. So discrete objects are used for what's known as nominal, and ordinal data. So these are discrete categorizations. Nominal data is where there's no natural order or ranking of the values. So nominal data would be, colors would be nominal data. So red, blue, green. There's no rank unless you're trying to rank them in terms of your favorite color or something. But they're really just categories. There's no natural ranking. Ordinal data, again, are categories, but there's a natural order to them. So low, medium, and high would be ordinal data. Even though it's categorical, it's still, you can still rank it. Okay. Again, in most cases, it doesn't matter in terms of how you structure your data model in a GIS context, but important to know the difference. So these are used for discrete entities, so buildings, land uses that have discrete, well-defined boundaries, anything with a well-defined boundary. So probably things like administrative units. So we've got borders of countries and local government areas and so on are an example where we have these discrete, well-defined boundaries. Okay. So that's the distinction between the two. Okay. So that's okay. Got that? Yep. The two different types of conceptualization. So then the question is, how do we go from the real world to a construct in a GIS to represent these objects? And I guess the way that this is done is taking the real world. So you take the real world, and we have what's called a GIS data model. So this is what we're going to talk about today. This is really a description and representation of that usually in a conceptual form. It could be boxes and arrows and diagrams, for instance. That gets represented as a digital representation of that conceptual model. We're going to talk about this today, and then tomorrow we'll talk more about that and how you collect data, and then it's used within a GIS to answer questions or make decisions and so on. So really, that's a process of increasing abstraction, essentially. So you have this idea that you start with reality. You have a conceptual model. So this is really just boxes. This might just be a description, actually, of what you're trying to do. There's some logical model that says how you're going to implement that in a GIS as a physical model in digital form. So this might be actual, the database structure that you're going to use. So we'll talk about databases early next week. So we'll see how databases work in a GIS. And so this might be the database structure, and then you actually implement that in a GIS as a physical digital model. And that's where you get the representation in a GIS. So, and this is really going from humans are very good at interpreting the real world. We see patterns and we interpret the real world, and that's partly through experience and partly through just the way our brains operate. And so we interpret the real world in a certain way, but we have to tell a computer how to interpret the real world. So this is very human-oriented. A computer can't really interpret the real world as it is. So we translate that into something that's more computer-oriented, and that's really the idea of that flow. Usually, we don't have to do this. A lot of this has been done for us. So we have some standard data models that allow us to do this very quickly, and we're going to talk about a couple of those standard type data models. So data models probably, the data models sort of fit in here. So this is the conceptualization of how we represent the real world. Okay. Right. So we're going to talk about two data models. And many of you who've used GIS would have come across these before, but I guess we're going to just define them formally. The two data models are raster, which are really a grid, useful for representing continuous fields. It's just representing the world as a grid, and then vector. And these you had some questions about this in the prac yesterday, so to get you start thinking about it. So I hope maybe some of you read some stuff about it. So we're going to look at those in more detail and really define what they are. But these points, lines, and polygons are useful for representing discrete objects. And in some ways, they are what they say they are. Okay, so so vector data models. So what I'm going to do first is just describe what a simple vector data model is. So these are, in ArcGIS, these are the shape files. So the shape files you used yesterday are essentially a representation of, a simple representation of vector data models. And they can consist of points, lines, or polygons. And I'll explain what each of those are in a moment. And basically what each point, line, or polygon contains is really information about the spatial location. When you look at that data in ArcGIS, the spatial location information is hidden, but there is a spatial location in there, in the database, and what it is. So this is an example here where we have, so the points basically are just a point in space. Points have no area. They're just a single point in space with a coordinate of where they are in space, and they'll have a description of what they are. So in this case, we've got points. These are hydrants in this example. So they'll have a spatial location. They have no area, and they have a data attribute, which is a hydrant. Lines, again, lines represent lines, as what you would expect. They are what they say they are. And they, again, have no area, but they're a linear feature. So in this case, these lines are representing streets. And again, these will have attributes. So you looked at, yesterday when you looked at your data on roads, each line or polyline had an attribute. And I think in that data set, the attribute was the street name. Okay? But they could have other attributes. They could say what the road type is or the size of the road, traffic volume. So there's lots of different components that you could represent in that as those attributes. And then these polygons here are property boundaries. And again, there might be attributes associated with these that represent, for instance, the property lot name or the property size and so on. Now, these do have areas, so a polygon has an area. So anything with an area, it should be represented by a polygon. Okay, make sense? Yep. Okay, so let's look at how they're represented. Now, in basically a GIS database, you can think of it as a spreadsheet that has information about the location of each object and has information about the attributes of each object. So we're just going to think about it as if it was a spreadsheet. And so we're going to talk about coordinate systems in the second half of this lecture. But essentially, the coordinate system can be thought of as an x and y coordinate. So you can think of a graph with an x and a y, and we can represent things as an x and y coordinate. It's a bit more complicated than that, but let's do that for now. And so how do we represent points? Well, we have points. They have no area. And we can just represent them as a table with point number and an x and y coordinate. So, and this can be represented in lots of different forms in a database. But here we just say point 1 is at location 0.24. Okay, I think it's x and y 24, and so on. Okay, so pretty simple. It's a simple point representation. Okay. Polylines are again can be ignore these lines here. Actually, I don't know why those lines are there, but this is one polyline along here and one polyline along here. So these can be called polylines or they can be called lines. Either. I think ArcGIS calls them polylines. And so in this case, we have a start and an end. But along that line, we have coordinates to represent how those lines are joined up. So polyline number 1 runs from here to here, is a coordinate of 1, 5, and then another point at 3, 6, and so on and so on. So it joins up a line and represents a line. So a line is essentially a series of points that represent that line. And you can think about this and think about, well, you could almost have an infinite number of points along here. So the complexity of which you can represent that line is almost infinitely, you can represent sort of infinite complexity, but obviously as you have more and more points, the amount of data you have to store and so on goes up. So there are limits, okay? Does that make sense? That's lines? Yep. Polygons are a little bit different. They in some ways, they look like polylines in their data representation. But the key distinction is the start point has to equal the end point. Because they represent an enclosed area, the start has to equal the end, right? So we start here for polygon 1, start here at 2, 4, and end at 2, 4. Okay, so the start and the end are exactly the same. So that's what makes it a polygon. Okay, so pretty simple. Yeah, makes sense. So in most cases, you don't have to worry about this. The GIS does most of this stuff for you. You don't really see it. But I just wanted to give you an understanding of what it looks like in terms of the data structure. Okay. So I mentioned this was really a simple representation of objects geographically in a landscape. But there is a thing that makes it a bit more complex, is a thing called topology. So topology basically tries to, in a vector data model, what it tries to do is define relationships between objects. And at the heart of it, topology says something about geometric characteristics of objects that don't change under transformation. So really it means if you sort of you shift these objects or move them or bend them in some way, there's some geometric or geographic characteristics that don't change. Okay? So there's some elements that don't change. And it depends on what type of topology you mean. Okay? But I'm going to look at 3 types of topology. And topology is useful when you're manipulating data or collecting data, but you want to make sure that certain rules about the defined relationships between objects are maintained. And the 3 types I'm going to look at are adjacency, containment, and connectivity. So, and these can be really important for things like correcting data errors that break certain relationship rules. Network analysis, topology is really important because it needs to ensure things are connected up. But let's just look at what these are, these 3 different components of topology. So adjacency topology basically says if you've got 2 polygons or 2 objects close to each other and they share a boundary, they must always share a boundary. So that's an adjacency thing. So you can set rules in a GIS that say A is adjacent to B. So if you have a data set and there's a boundary for B that isn't adjacent to A, you know there's an error. So very useful for correcting errors. So this could be a fence line between 2 properties. Obviously, there's not 2 boundaries. There's 1 boundary, and they share it. So you can enforce that with what's known as a topological relationship. Connectivity says that if you've got, say, this is a line, this line must connect to this line C must connect to A and B. Okay, really important for understanding networks, traffic flow models, and so on. This is really important because if this doesn't connect to A and B, and it's a road intersection, then your model's wrong. Okay, there might be no path to that road when there actually is. So that's connectivity. And basic containment says that in this case, the polygon B must be contained within A. Okay, so if you know it's a house on a property, the property can't be the house on that property can't occur outside the property. So if you have a data set where the house does occur outside the property, then the topological relationship would be broken, and you would know there's an error in your data. So often used quite a lot to fix errors, but also useful for things like network connectivity. Okay. So we're probably not going to do a lot in terms of topology in the course, in terms of practical sense, but important that you know about it. Okay. Okay, I'm just going to give you an illustration of topology. This is a donut and a cup. The topology is the same. Why is the topology the same? It's been transformed, but they both have the same topology. And what type of topology do you think it is? Can you see why the topology is the same? Sorry? Yes, it's containment. Why is it containment? The hole? Yeah. Yeah, that's right. So you have a hole here, and it's always contained within the shape, okay? So it's really, this is just the cup is just a donut reformed into a different shape, and that's the whole of the donut, okay? So it's essentially a containment topology, more or less. Good? Okay, so very quickly, how do we represent topological relationships in a database, a GIS database? So remember, for polygons, we have this idea that you're just representing the points along the polygons. Sorry, I'm going to talk about polylines here, actually. Polylines are represented as a series of points. So in this case, we've got a number of polylines, sorry, I'm getting confused. We've got polyline 1 to 6, I think, and maybe there's more. Anyway, so remember, the polyline is represented by a series of coordinates. But joined to this so this will be a table within your GIS, but joined to that table is a series of topological relationships. And in this case, what it's saying is what polygon is on the left and right side of those lines. So polyline 1 is here. So in this case, the polyline has a direction. Where's polyline 1? Try to find it. Up here. So polyline 1 goes from this point to this point, okay? So the left polygon is 1. So there's a polygon outside here, which is 1. And then the right polygon is 5. Okay, so these 5s. Yep. So this is polygon 5. So what it's saying is, on the left, the polygon on the left always has to be 1, and the polygon on the right has to be 5. And you can do that for all of your polylines. So you're really specifying that topological relationship, which must always hold. Okay, so what it's saying basically is that polygon 1 and 5 have to share a boundary. Okay, so that's the way that topological relationships are defined for vector data in a GIS. So as I said, we're not going to do anything with topology in terms of the practicals and the work you do, but it's important to know that it exists. Okay. Okay, let's talk about raster data. So that's vector data model for discrete objects. If now we're looking at raster data. Raster data is much simpler in a way. It's really just a grid of cells, okay? And these cells contain information about their spatial location and the value of that cell. A much simpler data structure than vector data. So, but in terms of storing the data, can be it can be more. I guess in terms of the size of the data, can be much larger because you have to have a value for every cell. Okay. I guess some key things to think about, which we'll talk about briefly, is what the size of those cells and the values that you contain within them. So you can change the size of that cell. So choosing the size of the cell is important. I mean, in general, the smaller the size of that cell, the better, because you're assuming that within the cell the world is uniform. It's all the same value. So if you wanted to represent the density of people within Brisbane and then use cells at a 5 kilometer cell size, you'd miss a lot of the heterogeneity in where people live within Brisbane. So the cell size is important. We'll perhaps touch on that a bit later. Okay. Okay. So So I guess there's several types of raster we can use. There's things that are called which we call base layers. So as you get familiar with ArcGIS, you'll see that when you add data, if you click on the right-hand side of the add data little icon, you can add base layers, and ArcGIS gives you a whole load of base layers that you can use. And these are not really interpretable data by GIS, but are useful for us for providing context. So in this case, we've got data that shows roads, but then an aerial photograph or satellite image below that helps us interpret that. So really useful for interpreting and understanding data. But it's a photograph. Photograph is a raster layer. We can represent raster data as thematic layers, and this is where the distinction between continuous and categorical get blurred. Okay. So in this case, there's land cover types. So these land cover types are categorical, but the values we're representing in our raster data cells are discrete. Okay, so I guess there's a blurring between categorical and continuous. Yeah, I think we often do this because, well, one reason we often get data from satellite imagery, which are raster data. But also it makes analysis simpler because the data structure is simpler. And when you do your project, you'll work a lot with raster data, but actually you could do exactly the same analysis probably with vector data. It would just be much harder. So actually, because of the simple data structure of raster data, it makes analyses much simpler. But you sort of trade something off for that. Okay. Surface layers. So these are the typical continuously variable surfaces, elevation, temperature, those types of things. And then the other thing we can use raster data for is really basically using them to represent attributes of features. So you can get geotagged photographs that have a geographic location, and we can add those as attributes to our vector data layers, for instance. So you can do that in ArcGIS. So if you have a photo of your tree that you're representing as a geographic object, you can add that photograph as an attribute. And obviously, the photograph is a raster data set. So how do we represent these things in a GIS? So again, it's a table, and so let's assume we've got this raster representation. Let's say it's ocean, tree cover, and urban. So we can represent these. These are discrete objects, discrete values. So we might represent them as values of 1, 2, and 3, and then essentially we just represent them as a series of values in a table. This thing up here just tells the GIS that it's a 10 by 10 grid, and there's 3 values. Okay? And then we essentially just represent all those values as rows in your database. Okay? Very simple. The actual data structure will look different to this depending on what GIS you're using, but the principle's the same. I'll just mention one thing. So as the cell size of a raster data set becomes smaller and smaller, the size of the data set becomes much bigger. And over large areas, it becomes computationally infeasible to do analyses and storage capabilities. You reach the sort of storage capabilities or limits to storage capability. So what I guess GIS professionals have been trying to do is, over the years, is try to work out ways in which to make those data sets smaller, okay? So to compress them, essentially, to make them manageable. And this is becoming increasingly important as we get much higher resolution remote sensing data and so on, and it becomes an issue. So, even doing things like mapping land cover or something, or some measure of land cover across Australia, say at a 1 meter resolution, is virtually impossible because it's such a large data set. So finding ways to compress data is important. So I'm going to show you one simple way of doing it. Again, we won't do this. There are ways of compressing data sets that ArcGIS gives you that functionality. But I just want you to see the principle. So again, let's assume that we've got, let's say this is a lake and this is urban. And we represent them by ones. I haven't shown the zeros here, but assume there's zeros in all these values. So ones and zeros. We've got a 10 by 10 landscape. Again, it's showing one value, so just showing the one value of this. And then what this does, it says, rather than having, so under the data structure I showed you here, there would be a bunch of zeros up here, okay? So you'd have 10 zeros. But what this is called run length encoding. What it does, it says there's a 0 value and there's 10 of them in a row. So that's telling the GIS there's a 0 value and there's 10 of them in a row on that row. And then this one says, so in this case, instead of 10 values, you only need 2. So you've reduced the amount of numbers you need to store by 80%. In this one, you've got 3 zeros in a row, 5 ones in a row, and 2 zeros in a row. Okay? And you've reduced the number of numbers you need to store by 40% in that case. So it's a simple way of reducing the amount of data you need to store. Okay? So when is this not going to be very useful? Or when is it most useful? Lots of, do you mean lots of? Right. Yes, that's right. So you'd have lots of variability. Yep. Lots of different categories. Yep. So if you take that to the extreme, if it's what's the extreme of lots of different categories? Yeah. So when every cell is different, and often if you're thinking of continuous values, then pretty much every cell is different, has a different values. In that case, this approach doesn't work very well. Okay. So there's things where it will. If you've got lots of repetition of values in a row, it works well, but otherwise it doesn't. Yep. Good. Excellent. Okay. So I'm just going to make the distinction. So that's raster data and vector data. But let's just quickly look at attributes. I'm just going to mention this to make it clear. So really, there's two types of attributes, and you might hear me talk about attributes. And hopefully I'll try and make it clear whether I mean spatial or non-spatial attributes. But for both raster and vector data, they have spatial attributes and they have non-spatial attributes. So with a vector data layer, they will have spatial attributes representing the location of the points that define points, lines, or polygons. And for a raster data set, usually there's a spatial location, which is, I think in ArcGIS, it's the top left-hand corner of the grid. And if you know the location of the top left-hand corner of the grid, and you know the size of the grid cells, you can work out the location of the center of every other grid cell from that. So you only need one spatial location. So that's the spatial attributes for vector and raster. But then there'll be non-spatial attributes. So usually with vector data, there's a whole range of spatial attributes you can add. So the data you worked with yesterday had, so you're working with local government area boundaries, and they could have had information about that boundary, that local government area, the name, and so on. And the roads had attributes as well, such as the name of the road. But they could have other attributes. So those are usually represented in a table, and you can visualize that table in the GIS. For the non-spatial attributes for raster is really the values of the cells, and it assumes the value of that cell is uniform across that grid. Okay, so if it's a big grid, it's going to lose a lot of the variability that's inherent, or the complexity that's inherent within the grid. Okay, so that's, if we talk about spatial and non-spatial attributes, that's really what we mean. And GIS is unique in the sense that we have that spatial component. So it's different from just a standard database. Okay, so I'm going to get you to do a little exercise now. So I want you to just work on in your tables, and we'll do this for about 10 minutes or so. I basically just want you to think of a question that GIS could help address. And it can be anything, whatever you're interested in. And then I want you to think about what's the appropriate temporal and spatial extents of analysis. So by that I mean, I'm going to talk a little bit about scale tomorrow, but how big a study area would it be? Would it be Brisbane? Would it be all of Australia? Would it be global? So how big and what time period would it be over? If you're thinking about things that change through time, Would it be over 20 years, 100 years, 5 years, and so on? But then I want you to think about what's the appropriate data model for that question. What type of data? You have to think about what type of data you might need. What's the data model you might use? And then think about what some of the limitations of that might be. So, you know, if you've got a really big area, and you're trying to capture something that's you know, varies a lot spatially, and are there limitations in the cell size, for instance, you could use for a raster representation of that data. So I just want you to do that in your groups, and I've printed some of these out, and you can just write in that, and then we might just maybe pick a couple of groups and see what you came up with. Okay, so let's do that for 10 minutes. Yep. Okay. Well, we'll see. We'll see how we go. Maybe you only need 5 or 10 minutes. So grab one of those. I'll leave that up there anyway. You can scribble on these. I'll give you a couple of these, actually. I'll give you a couple. Do you want 2 of these? Just to scribble on. You don't have to scribble. Yeah. There you go. So don't worry too much about the extent stuff. I want you to mainly think about what's the right data model to use for your question. Oh, yeah, yeah. I'm going to miss them all. So be it. Enjoy. Okay. Right, so I'm sorry I didn't get around to talk to everyone, every group, but who's got an interesting question they addressed or talked about? Does anyone want to volunteer? Or should I pick a group? But this group here, what did you discuss? Right, so you're thinking about distribution of species to identify protected areas, yep. Yep, yep, okay. Right, okay, yep. So you're representing biodiversity. What data model did you think was most appropriate in that case?
We think it's vector, but if the species will move around, then I think that Raster can also do
Mm-hmm.
to show the probability of what is the most highest place probability for them to show up.
Right, okay. So it sort of depends. So it could be vector or raster depending on what you're measuring? Yep, right. So if it was the probability of a species occurring, that would be, you're saying that could be more raster data. And the vector data would be what? Locations of individuals or? Okay. So you might have discrete locations of populations. Yep. Yep, I see. Yep. So it could be either in a way. Yep. Yep, good. What about one other group? What questions did you have?
So ours was where to locate a new national park in Queensland.
All right.
Protect koalas.
Okay, right. Same sort of question. Okay. And where was it? Okay. And so
So it'd be like a statewide scale.
yeah, okay.
And we looked at like annual climate factors,
Right.
like rainfall and
Yep.
topography as well.
Okay, yep.
So we would use the raster
Okay.
model.
So they'd be raster because they're continuous type variables. Yep, yep.
County distributions,
Mm-hmm.
population density stuff as well.
Yep, yep.
Actual koala population.
Okay, good, good.
And then we have limitations, like you might have too many data points, like you were talking about,
Right.
or just the accuracy of the data.
Yeah. Okay. So sort of your limitations were sort of constraints on data accuracy and availability and so on. Yep. Yep. Okay. Good. Yep. So I think I just wanted to spend that that exercise to really just get you thinking about how different data models might drive how you might tackle a particular problem with GIS. And you always have to make these decisions as you go along. Sometimes you're constrained by data. Sometimes the only thing you have is a data in a particular format. But I think you need to think about, is the data model you're using appropriate for the question you're answering and the data you have available and so on. So it was really just to get you starting to think about that. Okay. Right. Okay, any questions? Yep. Data models are okay. As I said, I don't cover everything in the lecture, but there'll be, if you do the readings, then there's more information in the readings. Yep. Oh yes, actually yes, I did. I was just talking to this group, and I said I should mention this, and I forgot. So you you can, yep. So there are ways, but each data set, each layer has to be one data model. So it's actually the data model that's defined in the database of a spatial layer is a single data model. So you can't have, for instance, you can't have a layer that has raster and vector data in it at the same time. They have to be separate layers. And similarly, you can't have a vector data model that has points and lines or polygons in simultaneously. They're defined separately as a point layer, polygon layer, or a line layer. So that's defined in the structure of the database that underlies a layer. What you can do, even though they're separate, essentially databases or layers, you can integrate them through doing various what we call overlays. And you can integrate vector data with raster data, and you can integrate different types of vector data with each other. We'll start to talk about that in the analysis sections of the course early next week. So yeah, although in terms of their database structure, they're separate, and they can be integrated. So yeah, and that's one of the, I guess, the power of GIS is actually integrating data sets together. So yeah, good question, and thanks for reminding me. Okay. So let's look briefly at georeferencing and coordinate systems. So we've talked about how you represent objects, but actually it's really important to know where something is on the Earth's surface as well. So how do we do that? And I've talked vaguely about XY coordinates and things like that, but what are they and where do they come from? So we're going to in this last 20 minutes or half an hour, we'll talk about two different types of coordinate systems. So coordinate systems are really things that tell us where something is on the Earth's surface. And we're going to talk about two types of coordinate system. One is called a geographic coordinate system, and one is called a projected coordinate system. Okay. So, and we often call this georeferencing, and this, I guess, this is just perhaps this just formalizes some of the definitions of what we mean by a coordinate system. So if you've got a spatial object that's georeferenced, what it means is that it has a spatial coordinate that's georeferenced to a unique point on the Earth's surface. Okay. And so there are certain properties that georeferenced locations should have. They should be unique, and they should be constant through time. Okay. So if a location changes through time, you have to know the date when it was collected or georeferenced. It doesn't makes life difficult. And if it's not unique, then a georeferenced location could be multiple places on the Earth's surface, and we know we can't be different places at the same time. So some simple examples of georeferencing are things like addresses. So addresses, when we used to use post, I guess we still do in a way, but addresses is essentially unique. You can post a letter or a parcel to an address anywhere in the world, and essentially, although there are some exceptions, will be unique. Okay, so that's a georeference location. Place names are essentially georeferenced. So if I said to you, "Where's New York?" most of you would have an idea where that is. Okay, so place names can be, although often place names are not unique. So it's not strictly a very good georeference system. But what we're going to talk about are what's known as coordinate reference systems. So these are things that are defined in terms of places on the Earth's surface that are usually represented by some sort of coordinate. And these are things like national grids, latitudes and longitudes, which you would have heard of. Okay? But there's two types. There's geographic and projected coordinate systems. Okay. All right. So the first one is a geographic coordinate system, and this is where really latitude and longitude come in. And latitude and longitude define unique points on the Earth's surface. And what they do is they preserve the shape of the Earth. So they're a location on the Earth's surface that takes into account the shape of the Earth. Okay. So longitude, I'll try and get this right. Longitude is the east-west direction. So these are lines that go around the Earth and identifying the east-west location. So longitude is measured in degrees, and you'll see in a moment why it's measured in degrees. And well, latitude and longitude are both measured in degrees. But longitude runs from minus 180 degrees to plus 180 degrees relative to the prime meridian, which goes through Greenwich in London. Okay? And latitude is the north-south location, and that runs from minus 90 degrees south and then to plus 90 degrees in the north. Okay? Now, I said that these take into account the shape of the Earth's surface, and actually what geographers have done have modeled the shape of the Earth. I mean, this Earth's not quite spherical. It's sort of a flattened sphere. And they reference this to a thing called a datum. And the datum is essentially you can read some of the more details. I'm not going to cover all the details of datums here, but I'm just going to say that it really essentially represents a model of the Earth's surface, more or less. There's more detail certainly in the Jensen and Jensen book on datums and how they operate. And the most common one that we use, the most common one we use is WGS 84, which is the World Geodetic System 1984, which is the most. There's lots of datums. People have modeled the Earth's surface and the shape of the Earth in different ways, but that's probably the closest to a standard datum that we use. And you'll see in a minute why the shape of the Earth matters. Okay. So how do we calculate longitude? Well, let's imagine we're looking down on the Earth's surface, and we're looking from the north, so that's the North Pole. Okay. This is a line, an imaginary line that goes through Greenwich in London. This is called the prime meridian, and you imagine the equator going around here, and we're at this point on the Earth's surface. Let's assume that. So if we want to measure longitude, all we do is draw a line from the point we're at to the North Pole, and then we measure the angle from Greenwich, okay? And plus this way and minus this way. So you can see now why it's an angle, okay? Yeah, make sense? Straightforward? Yeah. And that's the prime meridian in Greenwich, if you haven't been there. Okay, so there are two types of latitude that we can calculate, just to complicate things a little bit. And this is where the shape of the Earth matters. And so there's the geocentric latitude and the geodetic latitude. Okay, and I'm going to one of them, the shape of the Earth matters, and one of them it doesn't. Okay, but the geodetic latitude requires knowledge of the Earth's shape, so the ellipsoid, and uses this information about the World Geodetic System datum. Okay, so let's look at what they are. So if we first look at the geocentric latitude, again, now we're looking side on to the Earth. Okay, North Pole up here, South Pole here. This is the equator, and let's assume we're at this point here. Okay, now the geocentric latitude draws a line from that point to the center of the Earth, and then measures the angle between the equator and that line. Okay, so that's just a direct line from the location you are to the center of the Earth, and measures the north angle here. Okay. What the geodetic latitude do, which is the one we usually use. I mean, if we usually this is the measure of latitude that we usually use. You draw a tangent. So this is the tangent that makes a right angle with the surface of the Earth, and then you draw a line at that right angle through the tangent down to the equator, and then measure the angle. Okay, so it's a right angle line to the surface of the Earth. And in this case, the shape of the Earth matters, because if it was a sphere, perfect sphere, this line for the geodetic latitude will always go through the center of the Earth. But because it's a sort of an ellipsoid, it's a squashed sphere, it doesn't always do that. So the shape of the Earth matters. So the way you model the shape of the Earth makes a difference to that latitude. Okay. And then again, this angle goes from plus 90 to minus 90. So that's why it's an angle. Okay. Make sense? Yep. Okay. So in short, longitude measures east-west, and latitude measures the north-south. Okay? So really, from that, I just wanted you to get the concepts of how it's measured.
For this course, this really isn't over my head, but how much of this do we need to apply, or is it just getting an understanding that there's two types and how they're calculated or not?
You don't have to I won't ever ask you to calculate them, but you need to know the concepts of how it's represented. So you know that if you understand these diagrams, basically that's what I want you to the take-home thing. Yep. Yep. But you're always measuring the angle in terms of longitude. You're measuring angle between a line to the prime meridian, and then in latitude you're always measuring a line from the point relative to the equator. So you're just measuring that angle. This is covered also in the in the book as well. So if you need to go back and look at it in more detail, you can. Okay, so that's geographic coordinate systems. But there's another type of coordinate system called a projected coordinate system, which basically transforms a three-dimensional geographic coordinate system to a flat coordinate system. So if you think about latitude and longitude, it's a three-dimensional coordinate system in the sense that it just preserves the idea that the Earth is a three-dimensional structure and tries to locate, identify locations on the Earth's surface. Okay, but we commonly use projected coordinate systems, and what that does, it just transforms that three-dimensional structure onto a flat surface. Why might we even bother doing that? Yeah, so maps, yep. So yes, it's easier to carry around and store. Yep, that's a good reason. Yep. Anything else? Right, yes. It's much easier to visualize, isn't it, on a flat surface. Anything else? Okay. These are the reasons I have. Okay. We almost always view maps on a flat surface. Aerial photography and satellite imagery tend to be on flat as well, so we get a lot of data now from aerial photography and satellite imagery. And I guess, actually going back to this, we often use maps, okay, and now we use computer screens, but essentially we're viewing them on a flat surface. It's difficult, you can get globes and look at the Earth's surface, but it's not that, as you said, it's not that convenient. You can't carry a big globe around in your pocket. Increasingly, aerial photography and satellite imagery are used. They tend to be flat. This is a really important thing. Calculating areas, distances, angles and such is much easier on a flat surface because you just use Cartesian geometry or trigonometry. Otherwise, you need spherical trigonometry, which is much more complicated. Now, ArcGIS is moving towards just doing all this for you on the fly, but at the moment, a lot of what we do is in projected coordinate systems. But if we're looking at a small area, the world is essentially flat. So if we look out across to the paddock over there, or the running track over there, we don't see the curvature of the Earth. So with those small distances, it's essentially flat. So if we're looking at small areas, it doesn't really matter. The world is sort of flat. And many people still believe the world is flat. So, but it does raise some issues, and I'm going to show you a short video. So we're going to show you this video. And then I'll show you some projections quickly. But there doesn't seem to be any sound.
Hi, I'm sorry.
Hello.
Sorry to be late.
This is
I'm C.J. Craig.
Of course you are. I'm Dr. John Fallow. This is Dr. Cynthia Sales and Sir Donald Huke.
Huke?
Huke.
Okay, and you are the Organization of Cartographers for Social Equality.
Well, we're from the OCSE. We have many members.
How many?
4,300 dues-paying members.
What are the dues?
$20 a year for the newsletter.
Let's start.
Wait, I want to see this.
This is Josh Lyman.
Indeed you are.
Josh, this is Dr. Fallow, and
Hi.
who's Mary Men.
Yes.
Should we begin?
Yes. Plain and simple, we'd like President Bartlett to aggressively support legislation that would make it mandatory for every public school in America to teach geography using the Peters projection map instead of the traditional Mercator.
Give me $200 and it's done. Really?
No. Why are we changing maps?
Because, CJ, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
The German cartographer, Mercator, originally designed this map in 1569 as a navigational tool for European sailors.
The map enlarges areas at the poles to create straight lines of constant bearing or geographic direction.
So it makes it easier to cross an ocean.
But
Yes.
it distorts the relative size of nations and continents.
Are you saying the map is wrong?
Oh dear, yes. Look at Greenland.
Okay.
Now look at Africa.
Okay.
The two land masses appear to be roughly the same size.
Yes.
Would it blow your mind if I told you that Africa is in reality 14 times larger?
Yes?
Here we have Europe, drawn considerably larger than South America. When it's 6.9 million square miles, South America is almost double the size of Europe's 3.8 million.
Alaska appears 3 times as large as Mexico, when Mexico is larger by 0.1 million square miles.
Germany appears in the middle of the map when it's in the northernmost quarter of the Earth.
Wait. Relative size is one thing, but you're telling me that Germany isn't where we think it is?
Nothing's where you think it is.
Where is it?
I'm glad you asked. The Peters projection.
It has fidelity of axis.
Fidelity of position.
East-west lines are parallel and intersect north-south axes at right angles.
What the hell is that?
It's where you've been living this whole time. Should we continue?
Uh-huh.
So, you're probably wondering what all of this has to do with social equality.
No, I'm wondering where France really is.
Guys, we want to thank you very much for coming in.
Hang on. We're going to finish this.
Okay.
What do maps have to do with social equality, you ask?
She asked.
Salvatore Natoli of the National Council for Social Studies argues, in our society, we unconsciously equate size with importance and even power.
I'm going to check in on Toby.
Go.
These guys find Brigadoon on that map. You'll call me, right?
Probably not.
Okay.
When third world countries are misrepresented, they're likely to be valued less. When Mercator maps exaggerate the importance of Western civilization, when the top of the map is given to the northern hemisphere and the bottom is given to the southern, then people will tend to adopt top and bottom attitudes.
But wait, where else could you put the northern hemisphere but on the top?
On the bottom.
How?
Like this.
Yeah, but you can't do that.
Why not?
Because it's freaking me out.
Okay. So, what's the issue with translating the Earth's surface onto a flat surface? Yeah, distort stuff. So, as soon as you do the projection onto a flat surface, it's like it's trying to just stretch a ball out onto a flat surface. You've got to stretch it and bend it and perhaps break it. Okay, so that's what the trouble is. It distorts things, and it distorts things in different ways. And over the years, people have developed many different ways of transforming the Earth's the spherical or ellipsoid surface of the Earth onto a flat surface. This is the most simple. This is the plate carré projection, and basically just maps latitudes and longitudes directly onto an XY surface. And so what's an obvious distortion here? Sorry? Oh, Antarctica. Sorry, yeah. Yeah. So yes, Antarctica is just, it looks huge. It's probably, I suspect it's not that big. Okay. So there's distortions, especially in the north and south, so you get these massive distortions away, at least away from the equator. Okay. So what people have done is, actually, I should say it's actually called a projection because it's a bit like projecting a light through a transparent globe and projecting it onto a flat surface, and there's different ways of doing that. And people have used different methods. So and I'll show 3 methods here. So one is conceptually you have the globe and you project it onto a cylinder, and then you essentially open the cylinder out. So that's called a cylindrical projection. There's called a planar projection, which is basically take the globe and just project it directly onto a flat surface. And there's also conic projections, which essentially have, you can think of these things like cones wrapped around the Earth, and they project the Earth's surface onto a cone and then open the cone out. So if you, I think in the prac today, you look at a conic projection, you'll see it looks like when you look at it, it looks like an opened up cone. Different types of doing the projection. Now, they don't physically do the projection onto a surface, but they have mathematical transformations in the GIS that actually do the transformation for you into a new coordinate system. So you don't need to worry about how that happens, it just happens. Okay? So people have worked out how to do it. But what you do need to understand is what's the different types of projections that you can use. And I've listed these are the 4 main types of projections. And every projection usually tries to maintain one aspect of the geographic representation, but at the cost of distortions of other aspects. Okay? And so I'll just go through some of these. Okay? So if you come across a conformal projection, this really attempts to preserve shapes of the features. This is sort of, and I think as a consequence, it's sort of useful with navigation in a sense that it tends to preserve directions as well. So it preserves shapes, typically used for navigation. Equal area projection, this attempts to preserve areas of features. So it's really, if you want to calculate an area of something, then use an equal area projection, okay? But the cost is it distorts things like distances and shapes and so on. Equidistant, again, this is it is what it says it is. It attempts to preserve distances. So if your application is for calculating distances, use something like an equidistant projection. And then there's a final one here, which is two-directional or azimuthal. This attempts to preserve directions with respect to the center. And again, if you're trying to navigate from a particular location, and that's the center of the map, these true directional projections will be the one to use. Okay. So ArcGIS has a whole lot of functionality around these projections. I don't know how many projections it's got inbuilt that you can choose, but it's got a lot, and probably most that you'll need. And I think one of the nice things is that it has descriptions of what the projections do, what it preserves, what it distorts, and so on. So here's just a couple of examples. This is the Mercator projection they mentioned in that West Wing video. So the Mercator projection essentially preserves shape, but at the cost of distorting area. So you get those real, Greenland is massive, okay? So you get these big distortions. But shapes are quite well preserved. So that's why it was originally it was designed by European explorers to navigate, okay? And then you compare that to the Mulvide projection, which preserves area. So this preserves area. You see Greenland is much smaller, but it distorts shape, okay? So when you're looking at that globe, very different in terms of shape. So the shapes are distorted. Okay. And what I'm going to mention just before we finish up is and this is a commonly used one. So this is a commonly used projection for relatively local areas. So if you were doing something, for instance, the size of Southeast Queensland, for instance, or smaller, you might use this projection, and it's called the Universal Transverse Mercator. And basically, it divides the world up into 60 zones, and a north and a south. Okay, and what it does, it basically does the projection within each of those zones. So if you're within zones, it's conformal, so it maintains shapes, but there's really minimal distortion of areas and distances within zones. So as long as you're within a zone, then really it's a really good sort of general projection to use that preserves those areas and distances and shapes. But if you go across zones, it works very poorly. So if you're doing some global analysis or regional analysis across Southeast Asia, for instance, it would work poorly because you're going across many zones. Okay. So I'm not asking you in this course to remember every projection. I don't know. I use some common ones, and if I need to find out about what a particular projection that I need for a particular application, there's lots of resources in the ArcGIS help. So I'll put a link down here. In the prac today, you can explore that. I mean, I think the descriptions of the projections are quite useful, and they provide you with the detail of what the projection is. It'll say what it aims to preserve, what it distorts, and so on. So given the particular application, you can make an informed choice about what projection to use. So I'm not going to say anything more than that on projections. I think the key thing is to understand the concept, understand that it distorts shapes and areas and distances, and you need to choose carefully which projection you use. So I did have a little exercise, but I think I'm going to leave it because we've sort of, it's about, I don't think we really have time to do it. It was really just an exercise in thinking about trying to bring some of those ideas together about data models and projected coordinate systems. But you'll do some of this in the lab today. Okay, I'm going to leave it there. Any questions? So in the lab today, you use some data to explore the consequences of different projections and data models. So you'll build on what we've done today in the lecture. So I'll see you there in 10 minutes or so. Okay. If you have any questions, come up and talk to me. I'll be 5 or 10 minutes packing away. So.